Nanoswarms, microscopic robots capable of navigating inside the human body, have become a topic not only for scientists, but also for futurists, shaping tomorrow's visions. When this idea first emerged, it seemed like a scenario pulled straight from science fiction films. Yet today, rapid advancements in nanotechnology, biotechnology, artificial intelligence, and robotics are gradually bringing it closer to reality. Considering the size of the cells that make up the human body, designing machines at the scale of, or even smaller than, these cells carries extraordinary potential. Particularly in medicine, implementing such innovation could revolutionize disease treatment. Nanoswarms would not just target a single organ or tissue, they could operate throughout the entire body, coordinating complex tasks to address biological problems effectively. To understand this concept, it is crucial first to grasp what nanoswarms are. Also known as nanobots, these are robots produced on a scale between nanometers and micrometers. A single nanobot can perform a simple function, but when hundreds of thousands or even millions operate together, they can achieve highly complex tasks through swarm intelligence. The concept of swarm intelligence is inspired by nature. The way ants build nests or fish move in schools serves as a model for programming nanobots. With this approach, no central control is needed. Small units interact based on simple rules, producing large-scale outcomes. This makes the idea of using nanoswarms within the human body highly appealing. The body is a highly complex system, from blood vessels to neural networks, requiring flexible, adaptive, and versatile solutions to function effectively. One of the most anticipated applications of nanoswarms is cancer treatment. Current therapies like chemotherapy and radiotherapy target tumor cells, but also damage healthy cells. Nanoswarms, however, could be directed solely to tumor areas, potentially identifying and destroying individual cancer cells. This would minimize side effects while significantly improving treatment effectiveness. Moreover, nanobots could remove the waste left behind by destroyed cells, aiding the immune system. In this sense, they would act not only as destroyers, but also as microscopic maintenance teams that clean, repair, and regulate the body. This approach could revolutionize treatment not only for cancer, but also for vascular blockages, neurodegenerative diseases, chronic inflammation, and even cellular damage linked to aging. Another future scenario involves nanoswarms continuously circulating in the body, acting as an early detection system. Most diseases undergo cellular-level changes months or years before symptoms appear. Changes that doctors often cannot detect. Millions of nanobots patrolling the body could identify DNA damage, protein misfolding, or metabolic disruptions at very early stages. If this information is transmitted in real time, treatments could begin before diseases manifest. Nanoswarms would thus serve not only as treatment agents, but also as a biological monitoring system. Health would increasingly be defined by biological indicators rather than symptoms, enabling shorter, safer, and more effective interventions. Of course, realizing this vision requires overcoming numerous technological and ethical challenges. Firstly, materials used to produce nanobots must be biocompatible. Foreign objects entering the body are often perceived as threats by the immune system and may be rejected. Therefore, nanobots should be designed to be friendly to human cells, with some even mimicking cell membranes. Their energy source presents another challenge. Continuous external power supply is not feasible, so future designs may harvest energy from glucose, ATP, or other biochemical processes, allowing nanobots to function like cells. Communication is equally crucial. Millions of nanobots operating in sync require extremely precise communication systems. Magnetic fields, ultrasonic waves, or optogenetic techniques are among the proposed methods, though these remain largely experimental. One of the most fascinating prospects is self-repairing nanobots. The human body is a dynamic environment, with cells dying, regenerating, and undergoing biochemical reactions continuously. Nanobots may malfunction or lose functionality in such an environment. If they can self-replicate or repair themselves, they can sustain their functions long-term. While this sounds futuristic, nature offers proof of concept. DNA replicates to propagate organisms. Similarly, nanobots could theoretically rebuild themselves from basic components. However, uncontrolled replication is a serious risk. If left unchecked, nanobots could become a biological threat, emphasizing the need for strict safety protocols. Another speculative idea involves enhancing human capabilities with nanoswarms, not just treating diseases. Nanobots integrated into neural networks could boost memory, accelerate learning, and improve brain-computer interfaces. Those embedded in muscles could enhance strength, accelerate healing, or optimize performance in extreme sports. Advanced applications even include anti-aging solutions, nanobots repairing cellular damage, slowing telomere shortening, and maintaining protein function could allow humans to live longer and healthier lives. While this borders on science fiction, advancements in nanotechnology make such possibilities worthy of consideration. The societal implications of nanoswarms are also significant. Initially, the technology will likely be expensive, accessible only to the wealthy, potentially exacerbating inequality. While some benefit from nanobot-enhanced health, others may rely on traditional methods. Misuse is another concern. Maliciously programmed nanobots could target specific organisms or collect sensitive personal health data. Therefore, alongside scientific development, a strong ethical and legal framework is essential to ensure safety and fairness. Current experimental studies already show promising results. Some research uses DNA origami to construct nanostructures capable of delivering drugs to specific cells. Magnetic microrobots have been successfully navigated through the vascular system of mice. While human applications are still distant, these experiments demonstrate that the future is feasible. AI-driven control algorithms theoretically allow millions of nanobots to coordinate simultaneously, accelerating the transition from laboratory experiments to clinical applications over the next decade. Nanoswarms represent a new era at the intersection of biology and engineering. Humanity has historically battled disease with external interventions, drugs, surgery, or devices. Nanoswarms introduce the unprecedented possibility of internal, cellular-level intervention. This internal engineering concept could redefine the limits of human biology, making the body a system shaped not only by natural processes, but also by artificial design. In the future, humans could become stronger, smarter, and longer-lived, aided by microscopic swarms. A fascinating potential is the collective intelligence of nanoswarms operating across multiple bodies. Nanobots in the bodies of a community could communicate wirelessly, forming a large-scale health network. Infections could be detected before symptoms appear, providing proactive community-level immunity. On a global scale, such networks could mitigate pandemics by detecting and neutralizing pathogens early. While this seems utopian, the trajectory of biotechnology suggests it may not be impossible. In conclusion, nanoswarms microscopic robots are poised to play a transformative role in humanity's future. They could make disease treatment more effective, safer, and personalized. They could redefine human biology, extend lifespan, and transform societal health paradigms. Yet these possibilities come with serious risks and ethical questions. The development of nanobot technology is not only a scientific challenge, but a cultural and political decision shaping humanity's future. In the coming decades, we may all carry an invisible army inside us, constantly working, monitoring, and repairing. Through these swarms, humanity could redefine disease, aging, and even the boundaries of life itself. Immortality may lie hidden within armies so small they are invisible to the naked eye.